Hello, welcome back, 11th graders. So we are now moving on to the second half of our right triangle trigonometry section of this geometry unit. So what we are doing right now, we last class talked about the relationship of side lengths within right triangles. In other words, our three primary trig ratios, sine, cosine, and tangent. And we just talked about how to solve basic triangles from there. But we are in an applications course, and application courses is really about the word problems. And so the second half is really like the application side of it, which is where most of your IB questions are going to be coming from. We will not be doing a lot of questions like that bare, like just solving for pieces of right triangles, really at all with our IB questions. It's mostly going to be things like this. So being able to recognize the patterns that you see in right triangles, and then seeing that when you're talking about applications of them, that right triangles appear in all sorts of things. The first thing we're going to talk about is bearing. The bearing is like how you turn in relationship to north, south, east, and west. So when you have a 3-digit bearing, the idea is that you start with how you're facing, which is north. We always start with the north direction. And then that degree is how many degrees you're turning from north out, right? So like 90-degree bearing would be here. 180-degree bearing would be going directly south. A 90-degree bearing would be going directly east, right? So a 78-degree bearing, as we see in our example 5, is going to be something like that. So this idea is that the plane started at a true north, and then it turned at a 78-degree angle from north to go in its direction. And then we need to solve for pieces there. I'm going to draw a picture to help me understand with geometry. That's going to be a go-to for a lot of your problems. So we have this, we were going true north, and then we went at a bearing, 78 degrees, and we went that direction. So that means that this guy right here is 78 degrees. And it flies 400 kilometers at that 78 degree. So what it really means is that we go 400 kilometers and then we stop. So if we connect all of that together into one big piece of information, it means that we're talking about a right triangle. The due north versus the due east is encompassed in this right triangle. We went at a bearing of 78 degrees, and we did that bearing for 400 kilometers. How far north or south is B from A? So we went from city A to city B. So we started here at city A, went at a bearing of 78 degrees, and then went to B. So how far north or south is B from A? B is north of A, and we just need to figure out how far. North versus south is going to be that up and down aspect of the right triangle. So that means we're going to be solving for X here. Well, going in and labeling my side lengths, the relationships of my side lengths, remember that is what's key here. 400 is my hypotenuse. I know that this guy over here is going to be my opposite, which means that X is actually my adjacent. I want to solve for the adjacent, and I have the hypotenuse. So that means that I'm going to be dealing with cosine. Cosine of 78 is equal to the adjacent, which is X, over the hypotenuse, which is 400. Yeah, so solving for X, I'm going to go ahead and multiply both sides by 400. I get that X equals 400 times cosine of 78. And I get that X is equal to 83 does it say how many decimals? Nope. 83 we'll do 3 significant figures, 83.2 kilometers. So if we wanted to know how far north or south is city B from city A, you can say city B is 883.2 kilometers north from city A. How far east or west is A from B? A from B is going to be to the west of it. And so we are now going to be solving for Y up here. Now we'll be dealing with, we want to solve for opposite, and we have hypotenuse. So we're going to be dealing with sine. Sine of 78 is equal to opposite, which is your y value over the hypotenuse, which is 400. So I get that y is equal to 400 times sine of 78. And that is 391, sticking to my three significant figures. So I would say city A is 391 kilometers west from city B. It's all just right triangle trigonometry, but now we're just talking about applications. This is very, very common when you're talking about flight or ships in terms of bearing. Our second piece of application is going to be angles of elevation and angles of depression. So angles of elevation and angles of depression are about the relationship of what a person or an object spots, like either up or down from where their sight line is at. And that's a very typical mistake. Let's not get into mistakes. Let's just first talk about it. Getting ahead of myself. Nonlinear thinking. So we have a person. Hi. And that person has a line of sight. And that line of sight is always parallel to the ground. It's right out from their eyeballs. Now we have a line that goes up here. Actually, let's make that a different color. We have a line of sight that goes up this way. And your line of sight, if it goes up, is an angle of elevation. No, angle of elevation. And the angle is measured here from your horizontal up to the angle of elevation. That is how it is measured. Versus your angle of depression. Sorry, when I move that computer, I bet it's loud. Sorry. Your angle of depression is looking downwards. So you might be talking about an angle of elevation when you're looking to the top of a building, or maybe you're looking to the top of a mountain. When you're talking about an angle of depression, you're probably at a higher level, like maybe on top of a building and looking down, or on top of a cliff and looking down, or maybe you're on a lighthouse and you're looking at ships below, right? So this is your angle of depression. And again, built from your horizontal down. That is your angle of elevation, angle of depression. Realize from there, you can build in your right triangles by drawing in a line like that or drawing in a line like that, right? So then you can build in your right triangles in order to then solve for the missing side lengths or the angle if you need to. So the Burj Al Arab luxury hotel in Dubai, in the UAE, is located on an island 280 meters from Dubai Beach. A land surveyor who is 1.78 meters tall, standing on the shore of the Dubai Beach, measures the angle of elevation to the roof of the luxury hotel to be 36.6. How tall is that hotel? So there's a person. This absolutely needs to have a picture drawn first. There is a person. Oops, that's not what I wanted. And there is this luxury hotel. Obviously not drawn to scale. I actually don't even know what this looks like. I'm probably immediately after making these notes going to go look at this hotel and know what it looks like. But it's just your bare minimum drawing. And it says that it has an angle of elevation of 36.6. Remember that your angle of elevation is built from the horizontal line. Okay, so that is where your right triangle comes from, not from their feet. 36.6. Now, we have a few more pieces of information in here. We're told that the hotel is 280 meters from this beach that this person is standing on. So we know that the horizontal distance is 280 meters. So I'm going to go ahead and represent that in my right triangle. This is 280 meters. And then it says that that person is 1.78 meters tall. (1.78 meters tall). Now we want to solve for the height of the hotel. And the height of the hotel is this whole height right here. But my right triangle only encompasses this length of x. Let's draw that to be a little bit more clearly represented. That length right there is x, and we're missing the whole height of the hotel. So realize that the whole height of the hotel is also this piece right here, which is the same height as my surveyor, 1.78. So I know that the total height of my hotel is going to be that height that I solved for in the right triangle plus 1.78. With all of that, now I'm starting to develop a plan. I need to solve for x. Looking at my right triangle, I have the opposite. I want to find the opposite, and I have the adjacent. And as a result, that means opposite adjacent, I'm using tangent. Tangent of 36.6 equals my opposite side length, which is x, over my adjacent, which was what? 280. So solving for x, I got 280 times tangent of 36.6. I get that x is equal to 207.946, which means that the hotel height plus 1.76, right? 1.78. The height of the hotel is 209.7. If we're doing 3 sig figs, that means it needs to be 210 meters. Done.